Well, this one, last class we solved this beam case, this problem using our new beam governing equation, which is given in terms of a fourth order differential equation. And this one, on the left hand side, we have a clamped, and right hand side is subject to a supported by a simple support. And as I described, the first equations you need to start with is the governing equation. You have to write down EI V double force derivative equal Q. So I'm trying to emphasize that whenever you want to solve this problem in your final example, and you always need to start with EI V 1, 2, 3, 4 equal QX. Okay? That's the first equation you need to start with. And then QX is, what is QX in this case? Is Q0 and minus is a constant for X to over the region. And then you write down boundary condition. Here is the boundary condition at X equal 0. There's no deflections. And X equals 0, V prime equals 0. You have to write down this one first, okay? And X equals L, you have no deflection, and there is no moment applied there, right? So moment equals 0, and deflection is equal 0. So you have to start with those governing equations and forces, applied forces, and boundary condition. That you write down and then try to solve it, okay? If you don't follow this procedure, well, too bad. Okay, here is the procedure. Here is the procedure. EI with double prime, force prime, 4 times prime equal minus Q0, and integration there was a C1, right? There's a C1, and there is the C2. There's a C3, and there is a and C4, right? And don't pay attention. So this will be a C1, right? And it will always help all the constant which were already calculated here. But you need to start with this one and with the C1, 2, 3, 4, 5. Okay? Okay. Yeah, here is the procedure C1, 2, and if you interrogate, you have another a constant, and then C3 and C4, and boundary conditions and this. So this is the you have to start with. Okay. As I emphasized the last class, once you fill this one up to here, you have 50% of point. You don't have to get the, I assume you already know how to integrate them, and I assume that you already know how to get the C1, 2, 3, 4 by just using this condition. But keep that in mind, up to here you got half point. And if well, if you are asked to draw a deflection curve, sketch the deflection curve, you have to draw this one. If you draw this way, you got urong. you have to, this is certainly wrong, and this one you have to do this way, right? Because the angle is also 0. Keep that in mind. It's very important. This is the not quite right, and you have to do because the deflection and angle is 0, right? So you have to go this way, right? That's thing you have to pay attention. And here, moment is 0 and deflection is 0. Moment is 0 means that the angle should change. This one is not the vertical line. Okay, it's very important. So you should have these deflections like that. And again, if you have this vertical line like that, you will be wrong. And this one is also wrong. And again, you have to have deflection 0 and angle 0. And here, deflection 0 and this angle is not 0. Okay? Only curvature is 0. Curvature means that this one it has a curvature which you cannot clearly visualize, but you have to show this is there is some rotation. Okay? This is the deflection curve. And this is the old procedure. Now we are we're gonna examine some little advanced applications using beam theory. Let's say we have 2 beams, okay, 2 beams, and between these 2 beams there is this little support. Between those 2 beams, there is a support, and each beam and each end here and here, they are clamped. Okay, clamped. And here we have the support, and such that this beam, when this beam is subject to a force, then this will certainly deflect. But at the same time, there will be some support. How much the force, reaction force, which we don't know, right? We don't know the magnitude. And the force, whatever force support, that will apply to this bottom beam as well. So this force will cause deflections of the beam on the left-hand side. So now the question is we solve all the deflections and forces and so on. We got all the deflection curve, not only this, but also this beam. That's the questions. Clearly understood? Okay. Now, how to solve this one? Well, again, same thing. Exactly same thing. And the point here is that you need to point is that here there is the unknown force F. Not moment, only concentrate the force. There will be force, unknown force F between those 2 beams. And let's pretend we know this force. Okay? Let's pretend we know this F. And same force to here. Once we know the magnitude of this force F, then we should be able to solve this beam, right? Same for here. We can solve deflection here. Of course, in order to solve this one, we have to express this concentrated force P using in terms of what? distributed load Qx. That we will study today. Okay, using singularity function. Using singularity function, we should be able to express any vertical load, including not only distribute but also concentrate load, concentrate moment, and so on. So anyhow, the key point here is that, again, we just assume this is a known force applied to here, and then we solve this one. And here we know pretend to have this value, and then we solve it. And then, what is the condition we can make use of here? This deflection, whatever deflection we have at the contact point, the deflection should be same for this one and this one, right? So you get the deflection in terms of a V1, and you get the deflection V2, and at this point, you use the condition that V1 and V2 is the same. Using that condition, you can, what can you solve? You can get this F. Okay? You can get this F. Very important. This kind of a problem will appear in your final exam. And again, once you know this kind of a trick and understand how to solve this kind of problem, not that much difficult. Anyhow, before we move, I will get back to a chapter called about singularity function. Singularity function. This is a part of a beam theory, and singularity function is needed to express all this kind of discontinuous force and concentrate load and concentrate moment. Remember that the governing equations of beam theory is that EIV 4 times derivative equal Qx. What is the definition? What is the Qx? What's the definition of a Qx? Qx is the force per unit length. Okay? Force per unit length is not the force, is not the moment. It has to be force per unit length. And this one, well, from here to here, it is a force per unit length, but there is a discontinuous. And same here, this P is not force per unit length. This is just force, right? Concentrate force. And this is the moment, which is not a force per unit length. So we have to know how to express these kind of forces using in terms of force per unit length. That's the key point. Once we know, once we express them in terms of a Qx, which is a force per unit length, then we can solve that partial, differential equation. This is just some, I will explain this singularity function. Singularity function is usually this parenthesis, okay? Parenthesis with some power there. And some equation inside this parenthesis, and then some power there. So this is a we call singularity function, and we define this symbol. Okay, this is not regular parenthesis. This is the singularity function, and pay attention. There is n there, power, and there is a minus a. This can be any function, but typical form is the x minus a. Now, definition is like that. If x is less than a, means this is the negative, okay? If this is a negative, then this term, whole term, will be 0. And if this term is positive, means that if x is greater than a, then this term will be just regular parenthesis, power of n. Okay? It's simple. And if we, so using this definition, n can be positive or integer, including 0. Now, back to here, q0, x minus a, and 0 power means that if x is less than a, then no matter what power we have here, this whole term will be 0. So if x is less than a, this term will be 0, right? If x is greater than a, then this term will be just a regular parenthesis and 0 power, means that what does it mean? Exactly, 1. 1 times q0 will give us q0. Okay? So this definition will be useful to express this kind of a non-discontinuous function. So in problem, you will have this kind of a drawing, and you should be able to express this load distribution using this singularity function. Now, how about this one? Well, very much similar to this one, but there is the power of 1. Well, if x is less than a is here, then here, less than a, then this will be 0. No matter what power we have, is by definition, it will be 0. Now, what if x is greater than a? Then this power will be just regular parenthesis, and power will be 1, right? So it will become a linear function of x, and if x equal a plus L0, right? X plus L0, then x plus L0, and AA disappear, and L0, and power 1, L0, and Q0, right? So this is the way of expressing this 0 and linear. You can express many different types of a load. You can express parabolic, cubic, whatever order, power you want to describe, right? Okay, so far, not that much difficult. But the point is that once we express this one, remember how we solve beam, the beam differential equation? We have to integrate this qx, right? EI v 4 times equal qx, and we have to integrate 1 by 1, right? 1 by 1. That means we have to know how to integrate this singularity function. Singularity function. Let's put it this way. We have a function qx equal 0 and q0 if x less than a, x greater than a, which means that we have this kind of functions. This is a, and this will be Q0, and this will be L. Right? Let's just forget, try to not to use a singularity function, just regular expressions. Regular expression means that we have two expressions. One region is 0, and the other region is Q0. Now let's try to integrate them, Qx. You understand why we need to learn how to integrate this. But let's try to not to use a singularity function, okay? Qx, dx, let's integrate them. And then the procedure will be so that we just integrate this region and this region separately, right? So let's integrate the 0. C1, right? Just integration constant for x less than a. And Q0, you will have a Q0x plus C1 for xa. Simple, right? Now, let's try to use singularity function for this one. This will be expressed as Q0 x minus a 0, right? Am I right? Yes. Now, using this one, using singularity function, let's try to express this equation using singularity function. What will be the result? Remember that C1 is constant. So using C1, there will be C1 constantly. And then this Q0 will be just x minus a 1 Q0. Okay, let's check it out. Now, this one, if x is less than a, this will be 0, right? This will be 0. And so what? C1, only C1. Is that right? Yes. And now, if x is greater than a, then this will be some just x minus a, right? X minus a, and then little different, right? There is a qx, and there is the constant, and there is the Q0 minus a, and this will be a C1, right? So little different, but this C1 is the arbitrary constant. So if we from integrating from here to there, because this one we integrate this and come up with this one, then let's integrate from here to there. Integration will be like C1, we have a constant, integration constant, and then this 0 power. Okay, let's say we have just regular parenthesis, 0. How are you going to integrate? You just Q0, and there will be power of 1, right? Yes? Yes. So, in other words, let's integrate one more time. Integrate one more time, qx dx. And this will be c1 x plus c2, and q0 x squared plus c1 x plus c2 for x is greater than a, right? And this one, we can integrate directly from here. C1x plus C2. Actually, let me starting from here, C1. And this one simply square plus C1x plus C2. And if you compare the C1 and C2 is arbitrary constant, so this expression will be same as this one. So the point here is that once we define using this way, then integrations can be simply, you can do as usual. X minus a n power integration will give us n plus 1, and power will be n plus 1. Right? But you have to remember that n should be 0 or positive. Should be greater than equal to 0. And there is another expression when it's a minus, which is a little different. But back to here, this kind of concentrate load can be expressed, pay attention here, minus 1 and P here. Well, this one actually very similar to this load, and the width will be say delta, and this height. Now height will be load per unit length. So P over delta. So this, let's just pretend to have a new distributed load, and which has this amount and then this. And here, this is just a regular, force per unit length, same unit as Qx. It's not the concentrated load, but as a limit case. In this case, what will be the resultant force? Resultant force will be simply, this is the Q, right? Q times delta will give us the P. So if we limit delta goes to 0, then this will be smaller, and this magnitude will be larger, right? And finally, the integration of this Qx for whole region will be simply P. Okay, this kind of function is called delta function, singularity function or delta function, and that is simply we can use the symbol minus 1 here. P is a force, P and x minus a and power of minus 1. And there is the concentrate moment m0, then expression will be m0 and power will be -2. Just express them using these symbols, and then you follow this integration rule. Well, if x equal a, if n is power is less than 0, -1 or -2, then simply x, when x equal to 0, there will be no unit force is defined, right, at that point. But more importantly, if n is less than 0, the integration of this one will be x minus a, and then the power will be just increased by 1. There's no divide differently from this one. If you follow these rules, then you can express this concentrate force, concentrate moment. You just use this one, and then when you integrate, remember remember we have to integrate them. We just integrate the p, x minus a, and 0 power, and then integrate another one more time, and then from that time on, we just divide n plus 1. That's all the rules you need to follow. You need to remember. And another point is that here, the force P is the upward, and this is the positive P. And moment, usually this is the positive, but in here, by definition of this singularity function, this way, this moment will be positive here, just because of the definition. Okay, you have to remember these expressions, singularity functions, and for instance, well, this is not quite beam theory. This is how we calculate shear force and bending moment using those two force equilibrium equation. Here we have a concentrated force P here, then distribute load Qx is minus P x minus L over 2. L over 2 is where you apply load P, and remember there is the power of -1. Okay, power of -1, and then dv dx plus q equals 0, right? So we can simply have this qx here, and we can integrate to calculate the v, and integrate and give us, remember when we integrate, how do we integrate this one? Minus will be simply 0. Okay? And there is a integration constant. It's very straightforward and very easy to follow, very much similar to a regular parenthesis. And now how to interpret this expression? Well, by definition of the singularity, if x is less than L over 2, this will be disappear. And if x is greater than L over 2, this will be what? 1, right? It's 0 power. So that's P plus C1. And next step is, so, okay, here, that's why we got the V is C1 is simply minus P over 2 using boundary condition here. Boundary condition here. Boundary condition is the, from boundary condition, we can calculate the C1. C1 is the minus P over 2. Now, we have another differential equation to get the moment, and put it here instead of a V and integrate, and for V integrate, moment will be is equal P is not 0, is X just integrate. 0, just integrate x minus L over 2 and p over 2x plus C2, right? And integrate constant can be calculated using these boundary conditions, which is the moment equals 0. That means if you put x equals 0 here, and you have zero. So 0 minus L over 2, what this will be? This will be simply 0, right? Because this term is negative, and by definition, the negative of this one will be 0. So 0 plus C2 should be 0. So C2 equals simply 0. Now you got this one. And once you have this one, using this definition, what does this mean? This means that, again, 0 for x L over 2 and greater than L over 2, this is simply x minus L over 2, right? Using this definition, you can draw a moment diagram like that. So anyhow, this was the singularity function. And back to this chapter. We're gonna, let's solve this one using that singularity function. Okay, singularity function. And this is the one of the beam subject of this case, the right-hand side. And okay. Well, next one is the new problem. It's not the same as this one. So anyhow, for V1 to solve this one, solve this one, Gaboni equation is EI V1 equal QX, right? This is the Gaboni equation. Do not hesitate. You have to write down this equation, okay? Every time you have a beam problem, just write down. And then QX, in this case, QX given as P x minus, where is the P applied? Well, from here to there, there's a L over 4, quad over L, so x minus L over 4. And minus there. Minus is simply because it's a downward. And then there is the minus 1, power of minus 1, right? So this will be QX. Now, how about the boundary condition for this case? At x equals 0, what do we have here? X equals 0. We have force. Remember, we have to pretend we know this F. Let's assume this is a known force. So shear force is simply F. Shear force is the shear force is F. And here, how about the moment? Moment is 0, right? So we have a two boundary condition. V is given F, and moment is 0. And V is simply EI, V deflection, triple derivative. Remember, dm dx plus v equals 0. So v needs to be minus ei v1, 2, 3, right? And actually v here, v is given minus f. Should be minus because simply the force is applied upward, right? On the left-hand side. Remember the shear force is positive here and here. This is the positive shear force, right? On the left-hand side, it should be downward, but the left-hand side is upward, so shear force should be minus F, and V is the minus EI triple 3 times, so this is the what we get. Okay, I should write down again. V equal minus F, and this will be minus EI. So F equal EI V1, 2, 3. Okay? And moment. Okay, that is the moment is 0. Now, how about the x equal L here? What's the boundary conditions? Deflection is 0, and say again, what is 0 here? To prime equals 0, right? So one prime is missing here. Okay, prime is 0. And for V2, left-hand side, well, you may write down again EI V1, 2, 3, 4 equal QX. Well, you just say Q2. Here is Q1 and V1 and Q1. And here, do we have a distributed load? Simply no. So you write down Q2 equals 0. Right? Q2 equals 0. And now, boundary conditions is that at the left-hand side, V2 0, V2 prime 0, right? And the right-hand side, shear force V equal minus F because it's a downward on the right-hand side, and moment will be 0, right? This is the boundary condition, and from here we have the F equal EI V1, 2, 3, and V EI double prime equals 0, right? Okay. Well, up to here, you got the differential equations and forces, differential equation and forces and boundary condition, and forces and boundary condition. So up to here, I mean, this is the critical part. Now, how are we going to solve this? How are we going to determine F? There will be an important step called third one. V1 is what? This is the V1, right? And this is the V2. And here, V1 at x equals 0 will be same as V2 at x equal L. This will be same. So V1, 0, V2, L will be same, and you get the F. Right? If you wrote down this one, you got most of a score. Say 70 or 80%. Well, you need to proceed to solve, integrate this one. And since you have this singularity function, you can proceed to integrate 4 times, right? And those 4 constants will be obtained in terms using this 4 boundary condition, and same for here, and 4 boundary condition. And then using this geometric compatibility or geometric constraint, you have the f and you got all the equations. Okay, it's not difficult, but you have to be patient, follow step by step. Okay, don't get lost. Just pay attention and just follow the procedure. It will be a little complicated, but I'm sure you can get the solution. Now, next question, next problem is that, well, this is the just a demonstration of using singularity function. And the left-hand side, you have simple support and you have clamped. And x equals 0. Again, you need to start with Gabon equations, and Gabon equation EI 1, 2, 3, 4 and QX, and QX is simply this one. Right? And this is the boundary condition. At x equals 0, you have deflection is a 0 and moment is a 0. And x equals L, you have a deflection 0 and slope is a 0. So you integrate this one. Okay, minus 1, you integrate, you have just minus 1, change it to 0, and then C1x plus C2. And now here, integrate one more time. 1 will be a 2, and there will be divided by 2, right? That's the definition of a singularity function. And the other terms is same as the regular integration. And here, one more time, power of 3, and then 6. And you integrate. How do you get these all C? C1, 2, 3, 4? You're using these boundary conditions. How many boundary conditions? 4 boundary conditions. How many unknowns? 4. And then you can get all the C's and deflection. Now, let's say you are asked to calculate maximum moment. Where will you have the maximum moment? Maximum moment. How do you get the maximum moment? Well, once you have a C1, 2, 3, 4, back to here, this is the what? This is the moment. Am I right? This is a moment. Moment x is EI V double prime. That is the moment. And you have the C1 and C2. Right? Now you have a function. You have a function. How do you get the maximum? You always check the boundary and prime equals 0. Prime means that slope, either this point or that point, right? So you check the boundary, and derivative should be 0. You know what I'm trying to say? You have a function like that. Any function. You have any function like that. And you do not know, first you need to prime equals 0, which will give us this point, right? High hill or low hill. That's one thing. And also you need to check these two ends. because you don't know whether this or that. You don't know which one will reach the maximum. Right? So what is the m prime x? What is the m prime? Yeah, it's simply v, right? This is the m prime. So from here, 0, and then that's where you find this point, and then you need to check from this one. You need to check 0, you get value, and L, you get value, and then compare those 3 points, and that's the way you can find the location where the maximum moment occurs. The maximum moment is really important, because why is it important to get to know the maximum moment? Because whenever you apply force, not just concentrate, any load you apply, the failure always will occur at the point where maximum occurs. Okay? So finding that maximum location is very critical. Now, different type. Solving another equations. This one you have simple support and clamped and concentric load. Well, as you can see, the load you can have any kinds of this load, which you can express in terms of a singularity function. But here the point is that, there is the kinematic boundary condition, not ends in the middle of the beam, right? So far, we didn't learn how to solve this one. Well, one way could be like that. We just divide into 2 beams. Divide into 2 beams, and you solve this one and solve that one. But at the interface, this beam and that beam will have same deflection, same curve, same slope, and same moment, and these 4 conditions. So you solve this one and you solve this one, and when you solve, how many integration constant you're going to have? 4, right? If you solve this one, how many integration constant? 4. Totally you have 8 constants. Now, how many boundary conditions do we have? We have a 2 boundary condition here, 2 boundary condition here, and here at the junction, you have 4 boundary conditions, 4 conditions, so that we can solve those 8 constant using these 8 conditions. Very complicated. So, well, I don't want to use this one. I don't want to recommend this method. But this one is rather much simpler and straightforward. We just change this problem into here. At the support, we will have a unknown reaction, which is unknown. But let's pretend we have a known force. Just say F. Just say F. And once we know this P and F, can we solve these beam equations? Can we? Yes. We can. First of all, we express this P and F using singularity function, and we integrate 4 times. we get this using these two condition, we can obtain beam deflections. Now, how do we get this F? What is the condition at here? Any condition you can think of? Moment? Shear force? What about shear force? What about moment? The condition you know is that deflection is 0. Right? Deflection is 0, regardless this P. So once you get all the equation at x equals c, the deflection equals 0, then you can get the F. Okay? That's how you get F, using geometric constraint. The geometric constraint here is that simply here at V at x equals c equals 0. This way you get the F. Okay? And let's try to sketch the deflection. Okay? Sketch a deflection. Deflection curve. You will get this, and this, and this. Very important. You need to apply here. Then this end will be deflection 0, and deflection 0. But at the end is allowed to rotate, so rotate. And this one is allowed to rotate, so you need to rotate. But here, not allowed, and not allowed to have any deflection. So this one 0 and 0 slope, and goes like that. Pay attention. This one do not draw like that, okay? It's wrong, totally wrong. Always at the end is the vertical. Always vertical like that. Anywhere we have a vertical. Vertical is preserved. Well, strictly speaking, there is a little bit of a changing if we consider shear force, but here you don't pay attention to shear force. Okay. That's all. And strain energies, that's all for this beam theory. And strain energy is where I just go through. What is a strain energy? Let's back to a spring, which one is attached to a seal and ceiling, and then you apply load. And this force, P, when this one has a deflection up to x, then simply the force you need to apply is k times x. And this spring, this one, when you apply force P, and this force P has moved, which means that at this point, you give some work to this spring, and spring contains some energy. And this is a P, and this is X. See, at the very beginning, when x equals 0, there is no force. So the force will gradually increase along with x, because P is given kx, so increase like that. And energy, we call strain energy, contained in this spring up to here, this is called U. So U is simply x times kx squared half. Actually, this one comes from these equations, and this is a p, and this is x. So and p equal kx. If we put it here, we can get this one. And if we instead of x, p over x, we can put it here. Then we have this one. So this one is called strain energy stored in a spring due to a deformation. And now, this is the spring. Now, how about the elastic body, or a beam, or a shaft, a bar? What kind of energy will be stored? Will be stored in elastic body? Well, simply the form is given like that. Stress, we have a 6 component of stress and 6 component of strains, right? And sigma x times ex, sigma y, and you just multiply and integrate, and there's a help there, and this is the strain energy, similar to a spring. You have extension, a bar, and stress is simply P over A, and strain is P over A divided by E. So if you multiply this one, so P times 2, P twice, and E, A times, and help. And if you integrate them, volume, pay attention here, volume, okay, volume. What's the volume here? Volume is simply cross-section times length. And A, and this one you got here. And okay, why we the strain energy is important? Well, I cannot explain at this point, but when we drive a theory for finite element method or approximate method, the strain energy is very critical. Anyhow, once we get this one, the theory goes strain energy derivative with respect to P, you get PL over EA. Do you remember that delta is PL over EA? Yes. Now you get this strain energy, and all you need to do is just derivative U with respect to P. That will give us delta. You don't have to drive, go through lengthy derivations. All you need to do is using this stress, strain, and half, and integrate, and derivative. Same for torque. Torque is T, I, R, and divide G. Same, you just multiply and get the integrate. And remember, DL is the cross sections and lengths, and there is one I here. And once you get this U, the deformation, rotation is simply given as derivative of U with respect to T. And you get T or L over GI. Well, beam bending is the same thing. And sigma x is moment divided by IY, epsilon, sigma x E. And then you put it here, and 1 over half. And integration, you remember this L, volume is L times cross-section. And this is the cross-section moment of inertia. And this one will disappear. And how do we get the rotations at the here where you apply moment? You simply partial derivative, which will give us this one, and that's the rotations. So regarding the strain energy, you need to know, okay, this is the definition of strain energy, okay? Definition of strain energy. You have to understand this. And as I announced, this is the software you can download from our class website. And this is called Hybrid. Very important and very useful program to analyze the beam problem. And there is a step 1, 2, 3, 4. And very useful, very easy. And let's say you have a beam. You have a beam with very complicated cross sections. Okay, back to here. I will continue to this one to Thursday. But here, you just specify cross section, and here you just specify a coordinate. And here you just specify force. Don't pay attention to and then you click, you got the force. For instance, let's say you have I remember the first time I clicked this button and we got the solution. I just opened the solutions. Amen. Well, I will upload some simple method, the procedure how to use this one, and you will download it, and then this is the you got. This is actually, what is this? This is the wind turbine blade, and this one was just you calculate. Actually, this is a beam. We clamped here, and we applied the force. It's not just constant cross section. You can specify any cross section you like. Remember that step 1 is the cross sections, and step 2 is the coordinate. Step 3 is the force. And you get these deflections. And as you can see here, this line is the before deformations, and after load, it deflects this much. And you can see how much deflection you have, and you can have many different. This red cross section shows that this is the critical regions, most critical, because this one has the maximum moment, and this is the where maximum stress occurs. The sigma x. So using this tool, you will solve a beam problem and compare with your hand derivations. So anyhow, it's very easy to use, and it has a very different feature. You can create many different windows, and this shows how much it deflects. Well, this is not just a dynamic problem, but it's just, by animation, it gives you an idea how it deforms. Anyhow, I will continue to show more about this one, and the our class website, I will have a simple case, circular beam, subject to a concentrated load. Okay, let's say, circular beam or cross-section rectangular beam and subject to force, and you can solve by hand, and you can compare with this. Okay? Okay, so any question? Again, today's key point is the singularity function to express any different types of a load, and by integration that one, you will be able to solve deflection simply integrating 4 times of boundary governing equations. And another key point is that well, just a straight beam is easy, but if you have 2 beams together or extra constraint, then there are some methods and you can solve the beam using geometric constraint extra. Once you get all the equations and then using geometric constraint, you can solve the whatever external force you assume at the very beginning.